Hello, everyone. I'm Mamshad Rizve. I am going to present my PhD dissertation titled Annotation Efficient Visual Recognition from Semi-Supervised to Few-Shot Learning. Deep learning-based visual recognition have revolutionized many fields like autonomous driving, security, robot manipulation, home automation, manufacturing and quality control, medical imaging, to name a few. However, this progress has its own share of challenges. The major bottleneck in here is that these deep learning models require large amount of level data, which is very time consuming to acquire. For instance, if we look at this example, it's like a typical urban scene, which has several vehicles, trees, buildings. And now annotating this image will require like drawing complex contours. So even for an expert annotator, this will probably take several minutes. Now think about doing this for thousands, if not millions of images. It's also very expensive, especially for some domain-specific data. For instance, for medical data, it requires expert radiologists for annotations, of which the time is limited and they are also limited in number. Also, some of the categories are rare naturally. For instance, in here, you can see an image of sloth bear, and this is not like an animal you encounter every day. In parallel to that, these models struggle in open world setting because they need to know all classes in advance. For instance, if we look at this image, we see that there is a horse carriage on the highway, but the autonomous vehicle is kind of detecting it as a semi-truck. And this is expected because nobody will expect a horse carriage on the highway. Several research directions have been explored to solve this annotation bottleneck of deep learning models. One of them is transfer learning. So the main idea in here is that instead of training from scratch, we can pre-train a model on a related data set, which has a lot of label samples. So it can be something like ImageNet 1K or ImageNet 21K. Then we can fine-tune this model on the desired downstream data set with only a handful of label samples. Semi-supervised learning is another dominant approach for this, where we are given access to a handful of label samples, so which would be basically these color triangles in this figure, and bunch of unlabeled data, which are basically these gray circles. And the objective of semi-supervised learning is to propagate the knowledge from these label samples to these unlabeled samples so that we end up with good decision boundaries, eventually good model. Self-supervised learning takes a different approach where the objective is to pre-train a model to learn good representation on a lot of unlabeled data using some kind of pretest task. So that would be some kind of rotation prediction, solving jigsaw puzzle, or it can be using like contrastive, non-contrastive losses, or reconstruction-based objective like mass autoencoding. Then once that representation learning is done, we can quickly fine-tune that model on the desired data set with a handful of label samples. Few-shot learning takes a different approach where the main idea is to mimic human-like perception. So given some data from some scene classes with lots of samples, the objective is to recognize samples from new classes during inference with only a handful of label samples. So hence the few-shot part. Zero-shot learning is different. So different in the sense that during inference, we don't have any label samples for this setting. So in here, during training, what happens is that we'll try to align visual representation with some kind of textual description or list of semantic attributes. Now, during inference, given that new list of semantic attributes or novel textual description, we'll try to recognize new visual entities in a zero-shot manner. Active learning is an orthogonal approach where the main idea is to make the whole data annotation process efficient. So from high level, the idea is that we can start with some randomly selected label samples. We can train a model. Then with the trained model, we can compute some kind of utility metric on the unlabeled data. Then based on that utility metric and based on our annotation budget, we can select a subset and send it to the annotators. And we can repeat this process multiple times. So now let's come to the motivation. So the overarching motivation of this dissertation is to improve annotation efficiency of visual recognition model. To be particular, we want to improve semi-supervised learning to develop models which are less reliant on domain-specific knowledge and also suitable for uncurated open world setting. In parallel to that, we also want to improve few-shot learning performance. And in parallel to all that, we want to achieve competitive performance. So this is the outline of this presentation. First, I'll talk about our work titled Uncertainty-Aware Pseudo-Label Selection for Semi-Supervised Learning, where we'll improve pseudo-labeling for semi-supervision using uncertainty and design solutions which are domain agnostic. In the next work, we'll extend semi-supervision to uncurated open world setting, and I'll talk about our work, which is learning to discover novel classes for open world semi-supervised learning. The third work, we propose an improved solution for open world semi-supervised learning titled Towards Realistic Semi-Supervised. Finally, we'll focus on few-shot learning and talk about our work, which is invariant and equivariant representations for few-shot learning. Let's get into our first work, which is uncertainty-aware pseudo-label selection for semi-supervised learning. This work was published in ICLR 2021. Before going into our solution, let's look into the dominant approaches for semi-supervised learning. So consistency regularization is one of the dominant approaches where the objective is to obtain perturbation or augmentation invariant output distribution. Generally, these methods achieve state-of-the-art performance, but they rely on domain-specific heavy data augmentation. So naturally, it limits their applicability to a lot of other domains which are not image. So how this works is basically, given the label data, we can train a model using supervised loss, so that will be cross entropy loss. Then for the labeled and unlabeled data, for each sample, we can create multiple copies through stochastic transformation. Then once we get the output representation, we can minimize some kind of distance function between them to make it invariant to the input transformation. So that distance minimization can be L1, L2, KL divergence, any divergence function. Pseudo-labeling is another dominant approach for semi-supervised learning, where the objective is to generate pseudo-labels to incorporate the unlabeled samples into our training set. The main advantage of pseudo-labeling over consistency regularization is that this method does not require domain-specific heavy data augmentation. So they are applicable to most domains. However, the downside is that it performs poorly in comparison to the state-of-the-art consistency regularization methods. So how this works is basically, in the first step, given some label data, we can train a model using supervised loss. After that, we can generate pseudo-labels on all the unlabeled data. Finally, we can incorporate the labeled and pseudo-labeled data into our training set and continue training. And these steps can be iterated multiple times. So the objective of this work, to bridge the performance gap between pseudo-labeling and consistency regularization. So before going into our solution, let's look into what is the fundamental issue of pseudo-labeling. So it's kind of obvious because during pseudo-labeling, the training happens with small label data set. So if we want to generate pseudo-labels with that model, we end up with a lot of incorrect pseudo-labels. And training with those noisy pseudo-labels leads to suboptimal generalization, and we don't get good performance. Therefore, these incorrect pseudo-labels needs to be filtered out, and the conventional works try to filter them out based on the predictive confidence score. However, selecting pseudo-labels based on confidence scores is insufficient because neural networks suffer from poor calibration. By that, I mean that in neural networks, we can have very highly confident incorrect pseudo-labels. Therefore, when we are selecting pseudo-labels based on confidence scores, we still end up with a lot of incorrect pseudo-labels. However, another interpretation of calibration is that it represents network's overall prediction uncertainty. Motivated from this interpretation, in this work, we empirically analyzed the relationship between calibration and the individual prediction uncertainties. The results are reported at the right-hand side. So in here, the x-axis is basically showing uncertainty and y-axis is showing calibration error. We show results on two data sets, CIFAR 10, CIFAR 100 for different level speeds. So if we look at a particular point, let's say this point, so basically what we are seeing in here, that this point represents that for the samples which has uncertainty lower than this particular value, the calibration error this. So basically what this graph is showing us, at least the left side hand of this graph is showing us, when the uncertainty of the samples is lower, the calibration error is also lower. We build our solution based on this insight, and we want to select a subset of generated pseudo-labels with the following two criteria. First, the confidence of the prediction has to be high, and the network has to be certain about the output prediction. That means if the network is certain, the calibration error is lower, and since we already selected highly confident, they are more likely to be correct. We call this method uncertainty-aware pseudo-label selection, or UPS. So how this works is basically we generate pseudo-labels for all the unlabeled set. We select a subset from there based on the predictive confidence score. We select a more cleaner subset from there based on uncertainty. And these are our final set of selected pseudo-labels. However, this solution still has one problem. If we think about it, this is a selection-based method. That means we won't be selecting all the unlabeled samples. So because our network is not confident or certain about certain portion of the samples. To incorporate those samples into our training, we utilize the idea of negative or complementary labels. Basically, the idea is that even though the network is not confident or certain about a sample being present, it can be confident and certain about a class not being present. And we can use this information to select actually negative pseudo labels. And this gives us basically two benefits. First, we can utilize negative learning to improve single level classification. Next, it also allows us for multi-level classification, because in case of multi-level classification, we have to independently say which of the output classes exist and which does not exist. Let's look at a simple example in here. So let's say we have this dog image, and there are 4 possible classes in the data set, which are horse, dog, truck, and cat. Let's say this sample didn't get selected because the network was not certain and confident whether this is an image of dog or cat. But the network can be certain and confident that this is not an image of horse and truck. We can use this information and bring this image into training set. So this is our overall method for UPS. Given initially, we train the model using only the label data set. After that, we generate pseudo labels on all the unlabeled set. From the generated pseudo label, we look at the prediction confidence and also the uncertainty and select a subset where the prediction confidence is higher than certain threshold tau and the uncertainty is lower than certain threshold kappa. We add these selected pseudo labels to our training set and we continue this step. Now let's look into some results. So in here, we are showing results on standard computer vision benchmarks, CIFAR 10, CIFAR 100, with different portion of label data. So in here, we are showing results on CIFAR 10 with 1,000 labels and 4,000 labels. We compare results with other existing pseudo-label-based methods and also consistency regularization-based method. We see that our method outperforms this. We also see similar trend in CIFAR 100 data set. And now we mentioned that before we mentioned that our proposed method is domain agnostic. So we extend our method in a video action recognition data set, UCF11. And we see that even on this data set, our method outperforms existing solution by good margin. We also show results on multi-level classification data set, Pascal VOC, and obtain good results on this data set. Now, so let's look into some analysis. So for uncertainty computation, in our method, we mostly use MC dropout, but this MC dropout can be replaced with other uncertainty estimation methods, which can be MC spatial dropout, MC drop block, or even we don't do any changes in network parameter. We can generate the uncertainty from data augmentation. We don't do any hyperparameter optimization for these experiments, and we see that all of these actually leads to a similar results. So this kind of shows that our method is compatible with a lot of uncertainty estimation methods. This is an analysis for data augmentation. So our pseudo-labeling based solution does not rely on data augmentation. So in here, we perform a restrictive experiment where we don't use any input data augmentation. And we compare our method with 2 consistency regularization based methods. And we observe that our method outperforms them by very large margin. We do a different experiment in here where we are using stronger augmentation, which we don't use in our standard settings. So in here, we are using mix of augmentation, and we see that our method actually improves more than 2%. So this kind of shows that if we have access to stronger data augmentation, our method can take advantage of that and can have further improvement. This is an analysis where we show how robust our method is for hyperparameters. So one of the primary hyperparameters in our method is the threshold for uncertainty. In here, it shows that for a large range of uncertainty values, it reaches to similar results. One question can be there that this method has 2 hyperparameters. One is for confidence, one is for uncertainty. How do we actually select that? So this is basically an analysis for that, where we perform analysis on a small validation set on CIFAR 10 and actually plot the accuracy curve over different values of different thresholds of confidence. So we see that if we look at this analysis and probably would have selected a threshold, probably 0.7 or 0.75. And we can, if we look at the uncertainty distribution, we would probably selected something around 0.05. This is very important because once we do the same analysis for all the unlabeled data, we see the same pattern. That means that even on a drastically different data set, we can use only a small validation set and still come up with these hyperparameters, and our method can still scale there. So to summarize, in this method, we introduce UPS, a simple and efficient framework for effective pseudo-labeling based semi-supervised learning. UPS competes with state-of-the-art consistency regularization-based method without inherently relying on strong data augmentation. We are the first to propose negative pseudo-labeling for semi-supervised learning. UPS is versatile because it is domain agnostic and be easily used for multi-label classification. This concludes our first work, which is uncertainty-aware pseudo-label selection for semi-supervised learning. But this work has some limitation, like all works. So the major limitation this work has, same as most of the semi-supervised method, that it assumes the labeled and unlabeled data come from the same data distribution. However, this constraint is very difficult to satisfy in real-world scenarios because we have little control over the data collection process. And also recent works suggest that the samples from these unknown or novel classes deteriorate the performance of the semi-supervised method. Therefore, recent works try to mitigate the negative impact of novel class samples. In our next work, we address this issue and extend semi-supervised methods in the open world setting. And I will talk about our work, which is learning to discover novel classes for open world semi-supervised learning. This work was published in ECCV 2022. Let's look into the problem setup for open world semi-supervised learning. So in open world semi-supervised learning, we are given access to a set of scene classes with some label samples. We are also given access to a set of unlabeled samples, in which we have samples from the scene classes. So the scene classes in here would be cheetah, octopus, and elephant. And we also have some samples from novel classes, which are highlighted using the red squares in here. For instance, we have samples from class dolphin, frog, and zebra, for which we don't have any labels in the label set. Now, the objective of open world semi-supervised learning is to recognize the samples from the scene classes and also to cluster the samples from the novel classes. Therefore, the objective of this work is to classify or cluster novel class samples. And since it's a semi-supervised method, also to improve the performance of known classes utilizing the unlabeled known class samples. And our proposed method from high level has two stages. In the first stage, we learn to discover novel classes by utilizing three objective functions, which are pairwise similarity loss, entropy regularization loss, cross entropy loss. And once we learn to recognize or discover novel classes, we transform this problem to a closed-all semi-supervised learning problem, where we first generate pseudo-labels, then we can utilize any off-the-shelf closed-all semi-supervised learning method. However, some of these pseudo-labels will be noisy. Therefore, we introduce an iterative pseudo-labeling method in this work. Now I'll go into the details of our solution and talk about discovering novel classes phase of the training, particularly our pairwise similarity loss. If we think about it from very high level, discovering novel classes is an unsupervised clustering problem. And in any clustering task, the pairwise relationship basically determines the cluster membership. If we look at this example, which has 3 clusters with multiple samples, and we look at the pairwise relationship, there is only 2 possible pairwise relationships. Either they belong to same class or they don't. We can utilize this interpretation in case of neural networks as well, where we can determine the pairwise relationship from the similarity of output probabilities. And this is very beneficial for us because we can perform cluster assignment based on the maximum output probability. So we don't need to perform any clustering step. The clusters can be formed from the output probabilities. However, this task is difficult because training the network to solve this task is difficult because we don't have any ground truth labels. To solve that issue, we introduce a similarity prediction network to generate this pairwise similarity scores. Once we have those scores, we can use them as ground truth to train the actual network to perform this task. And for our pairwise similarity loss, we compute L2 loss between the cosine similarity of output probabilities and output from the similarity prediction network. However, optimizing the parameters of the similarity prediction network without accessing the ground truth levels is non-trivial. To address this issue, in this work, we make a design decision where we want to update the parameters of the similarity prediction network in such a way that it should not decrease the performance on known classes. Particularly, we update the parameters of the similarity prediction network using a bi-level optimization rule, which performs implicit optimization based on the cross entropy on label sample. Hence, the performance should not go down on the label samples. Well, pairwise similarity loss gives us the opportunity to discover novel classes. However, there is a case where it leads to a trivial solution. That means all the novel classes kind of collapses to a single class. To avoid this degenerate solution, we incorporate an entropy regularization penalty. Particularly, we perform entropy regularization over an aggregate statistics of the batch. So basically, marginalize the batch probabilities across the batch dimension and perform entropy regularization on top of that, which gives us which avoids the case where a single class will dominate the batch while making the individual probabilities output probabilities confident. Since this is a semi-supervised paper or semi-supervised work, we want to recognize the samples from the seen classes. So the typical way to do that would be we use available ground truth levels from the known classes and train it with the cross entropy loss. However, this solution is not optimal because it is sample inefficient. We won't be using a lot of unlabeled samples. Also, it will create a strong bias towards the known classes because we have stronger signal only for the known classes. To avoid this issue, we generate pseudo-labels for all the unlabeled samples. Once we have the pseudo-labels, we can train the network using cross-entropy loss, using both ground truth and pseudo-labels. So this is basically our overall solution for learning to discover novel classes phase of the training, where given some labeled data and some unlabeled data, we pass them through a feature extractor F theta and obtain some feature representation. We pass those feature representation through the classifier F5 to obtain the output probabilities. We compute pairwise cosine similarity between the output probabilities to get our pairwise relationship. We also pass pair of features through our similarity prediction network F omega to get the pairwise similarity score prediction. We compute our pairwise similarity loss, which is a L2 loss between these two similarities. We also compute cross entropy loss and entropy regularization penalty on top of the output probability scores. We combine these three losses and update only the parameters of the feature extractor F theta and classifier F5. Note that we haven't updated the parameters of our similarity prediction network F omega yet. To do that, we perform another forward pass only on the label set with the updated parameters of F theta and F5, and we compute cross entropy loss in there. We update the parameters of F omega using bi-level optimization with that cross entropy loss. Once we learn to discover novel classes, we can basically generate pseudo-labels for the novel classes. And this basically then, if we can generate pseudo-labels for novel classes, we don't have any notion of novel classes anymore. And we can utilize any off-the-shelf closed-all SSL method in our work. However, some of the pseudo-labels will be noisy. To address this issue or to mitigate that noise, we introduce iterative pseudo-labeling, where we basically iteratively update the pseudo-labels to mitigate this effect of noise. So it kind of works like expectation maximization algorithm. So where we are using our latest model to update the pseudo-labels, that means the expectation step. Then subsequently, we train the network with those generated pseudo-labels. That means the maximization step. Here are some results on 3 standard data sets, which are CIFAR 10, CIFAR 100, ImageNet 100. Let me explain the experimental setup a little bit. So in this experimental setup, we are assuming 50% classes are novel. So by that I mean that in case of CIFAR 10, 5 classes would be seen, 5 classes would be novel. And from those seen classes or known classes, 50% data would be labeled. So the semi-supervised part. And we report accuracies for only on the known classes, on the novel classes, and we also report clustering accuracy on all the classes. We compare our result with state-of-the-art method, ORCA, and for closed-all SSL method, in here we use mix-match and UDA on top of our method. And we observe that on CIFAR 10 dataset, our method outperforms the state-of-the-art by more than 5%. We observe an even larger improvement on CIFAR 100 dataset, where it outperforms the state-of-the-art by 8%. We also see a noticeable improvement on the challenging ImageNet 100 dataset. We also report results on tiny ImageNet dataset, which is harder because it has 200 classes from ImageNet. Even in here, we see that from second-base method, our method actually improves a lot. We also report on fine-grained dataset, Oxford PET, also see good improvements in here. We also reported results on SBHN dataset, while we are using only 10% label data instead of 50%. We observe good improvement on this dataset. We report results on additional 3 datasets, which are aircraft, Stanford cars, and Herbarium 19, and compare our results with the state-of-the-art ORCA. Note that Herbarium 19 has more than 600 classes, and it has real-world imbalance in it. So this is an analysis where we are trying to show the effectiveness of our pairwise similarity estimation method. So in our work, we introduced this network F omega to estimate the pairwise similarity scores. So in here, we look at the alternate solution, which we could have done instead of using this pairwise similarity network. So those would be if we don't use any similarity computation, or we use cosine, we compute cosine similarity from the features and use that as our pairwise similarity scores, and we could have threshold it. And all these solutions has been explored in related literature. And this second last row is the nearest neighbor. So basically, this is from the state of the art, where basically we try to mine the nearest neighbor from the mini batch and treat that as the similar pair. And we see that even when we do one-to-one comparison with that solution, our proposed method have significant improvement on novel classes. This is an analysis for computational cost, where the star actually represents the compute time for the state of the art. Since they rely on self-supervised training, it takes 28 hours to train in our system, whereas our solution outperforms it in 3.5 hours, and longer training improves the performance further. So to summarize, in this work, we propose a novel solution for open-world semi-supervised learning. Our pairwise similarity loss does not rely on self-supervised pre-training, which is the case for state of the art. Our pseudo-level based learning transforms open-world problem to a closed-world problem, which can give us further improvement. We introduced iterative pseudo-leveling to address the noise present in pseudo-labels. Our computational cost is lower. We also outperform current state of the art on multiple benchmark dataset, probably 9 to be exact. So this concludes our second work, which is learning to discover novel classes for open-world semi-supervised learning. However, this work has some limitation. So one of the major limitation is that the number of novel classes in this work needs to be known in advance. And also the entropy regularization loss, which we use to avoid degenerate solution, assumes the underlying distribution of the data is balanced or uniform. Also, this solution has multiple objective functions, and the training has 2 stages. We introduce our third work, which is towards realistic semi-supervised learning to address this limitation. This work was published in ECCB 2022 and was selected for oral presentation. From high level, this solution has 2 steps, not stages. So one is pseudo-label generation, where we generate pseudo-labels for the unlabeled data by using Singhorn-Knopf algorithm while taking class distribution priority into account. Once we have the pseudo-label generated, we perform reliable training with the generated pseudo-labels while taking uncertainty into account. Now let's get into the details of our method, and I will talk about our class distribution aware pseudo-labeling. So in our work, we want to generate pseudo-labels for all the unlabeled data. And once we have the pseudo-labels generated, we can just train the network using cross-entropy loss. So this becomes very easy, but it's not actually, because generating pseudo-labels for unknown classes is a complex problem because we are dealing with unknown classes. So to guide the pseudo-labeling process and to make the task easier, we need to inject some kind of inductive bias. Particularly in this work, we utilize class distribution bias for pseudo-label generation. So by that, what I mean here is that let's assume these are the pseudo-labels, that means y tilde for a particular class J. So we want to generate pseudo-labels in such a way that a number of generated pseudo-labels in a particular class J is equal to the number of samples present in that particular class, that means NUCJ. And this constraint pseudo-label generation is an instance of transportation problem, which can be formally expressed by this, where A is the transport matrix, which shape is NU times C. NU is the number of unlabeled samples. C is the number of classes. Now, if we look at the constraints, in here, if we marginalize across the rows, it returns a vector, where each element is basically the number of samples present in that particular class, hence in accordance with our class distribution bias. If we marginalize across the column, it returns 1 because it's a probability distribution. And this division by NU is to make it a joint probability distribution. So this is basically our optimization target for optimizing this pseudo-label generation process. And before trying to describe this, let us just look at it, a simple 2x2 solution for this. So this is basically cross entropy cost between the generated pseudo levels from the network, that means YU hat, and the transport matrix AT. Given the constraint, it is member of the transportation polyton. However, we still have a problem with this. It's mostly because we are dealing with unknown classes. So if we think about it, we are trying to take advantage of the prior class distribution. And we have only access to one set of prior class distribution. But since we are dealing with unknown classes, the network can learn to cluster these unknown classes in any order. That means this prior distribution we have access to is not valid since the network learns it in an arbitrary order. To address this issue, we introduce a permutation matrix PPI, which basically aligns our known class distribution prior with the data during training. And this would be our final optimization target. We solve this problem using Singh-Hornop algorithm. And this is a well-known algorithm for solving this constraint optimization problem. And to tie everything together, let's look at a very simple example. So we have some unlabeled data, we have the network, and let's assume we have 4 classes, which are C1, C2, C3, C4, and we have 4 samples, I1 to I4. And let's assume the first 2 classes are known and the last 2 classes are unknown. Without any constraints, the network will only generate pseudo labels for the first 2 classes because the network does not have any notion of the unknown classes. However, after applying our Singh-Hornop algorithm while taking class distribution prior into account, we'll be able to generate pseudo labels for those unknown classes as well. So this is basically the main idea of the pseudo label generation. Well, in our in this work, we are actually generating these pseudo labels employing the output probabilities. However, therefore, the final performance will be affected by the reliability of the pseudo labels. And the pseudo label reliability can be improved by incorporating predictive uncertainty. Therefore, in this work, we basically perform Monte Carlo sampling to measure the uncertainty. So what we do is we perform stochastic data augmentation to input and look at the variance of this multiple stochastic forward passes and treat this as a notion of uncertainty for a particular sample. Now the question is, let's say we have this uncertainty measure, how do we use that in our work? So one solution would be to filter samples based on uncertainty, as done in the first work. However, this has 2 shortcomings. One, it is sample inefficient. Also, we have to come up with the hyperparameters. To avoid this, in this work, we use those uncertainty scores, that means UX in here, as a temperature for the softmax probability computation. So basically, let's look at a simple conceptual diagram for this. So let's assume we have these 3 samples, and these are the typical softmax probability scores. And these are also the corresponding uncertainty scores. In here, the lighter color means lower uncertainty, and darker color means higher uncertainty. So what will happen after performing our uncertainty guided temperature scaling is that the sample for which the uncertainty is lower, it will get sharpened, and where the uncertainty is higher, that means the last row, it will get flattened. So this is basically our overall method. So let's say we have given access to a set of unlabeled data. We create 2 transform versions of those unlabeled data. Then we generate our class distribution, our pseudo labels, by using class distribution prior and Singh-Hornop algorithm. From there, to enforce predictive consistency, we solve those pseudo labels and call this step cross pseudo labeling. Finally, to encourage confident learning only on the novel classes, we'll binarize some of the pseudo labels if the confidence on one of the novel classes is higher than a certain threshold. After that, we perform mix-up augmentation between labeled and unlabeled data. We pass them through our network and perform uncertainty guided temperature scaling. Since we perform mix-up augmentation at the input, we also mix the final pseudo labels and the ground truth labels. Then we optimize the parameters of the network using cross entropy loss. So here are some results on CIFAR 10, CIFAR 100, and ImageNet 100 data set. The experimental setup is similar to the previous work. Only change in here is that we are using only 10% of the data as labeled. So we see that on CIFAR 10 data set, our method outperforms previous best ORCA by around 8%. We almost see like 17 to 18% improvement on CIFAR 100 data set. Even on challenging ImageNet data set, we see around more than 5% improvement. We also report results on tiny ImageNet and see very large improvement. Also on 3 fine-grained data sets, which are Oxford PET, aircraft, Stanford cars. And all of these data set, we see significant improvement over the second best method. Now, if we think back about the limitations of the second work, these were the 4 limitations. We have already taken care of the 2. That means this work does not require multiple objective functions, and the training does not have 2 stages. Now let's focus into the 3rd limitation. That means the number of novel classes needs to be known in advance. To address this limitation, in this work, we propose a simple method to estimate the number of novel classes. So in simple terms, what happens in here, initially we obtain some kind of self-supervised feature. So it can be SimCLR, it can be Dino, it can be Moco, any self-supervised feature. After that, we want to perform k-means clustering, where we vary the value of k, starting from the number of sim classes to a very large number. And the start from number of sim classes because we know that dataset at least has that many classes. Then once we perform the k-means clustering, we can compute clustering accuracy on the label samples because we have some label samples. However, all the label samples won't be clustered correctly. Therefore, we reassign the wrongly assigned label samples to their nearest label cluster, and we compute the accuracy again. And we call this accuracy after reassignment. We take the average between these 2 accuracies, so before and after reassignment, and we pick the k with the best accuracy and assume that the data set has that many classes. Here are some results for our estimation method on 4 data set, and we observe that our estimation method actually returns reasonable scores on all these 4 data sets, even when the number of classes is high. So we have taken care of 3 of the limitation. Now let's focus on the case where the method can only work on uniform data distribution. To address this, we extend our method so that it can take advantage of arbitrary class distribution. So basically for that, what we do is we train the model assuming that the underlying data distribution is uniform. After that, we obtain the posterior class distribution from the trained model after the warm-up report. So basically, we are trying to bootstrap the model's prediction to train it further. Then for till end of the training, we use the latest posterior class distribution as our prior class distribution, and we continue training. After every p epoch, we repeat step 2. That means we update our prior. So these are some interesting results in here. So we want to show results on imbalance. So CIFAR-10 dataset itself is naturally uniform. So we actually introduce the imbalance in here with an imbalance factor of 10. It means that the majority class has 10 times more sample than the minority class. So in here, we are showing that if that is the case, what would have been the results if we only use the uniform class distribution prior? Then the second row is basically showing that if we knew the ground truth imbalance in advance, what would have been the performance? So the second row shows that, okay, it improves over the case when we are using uniform class distribution prior. So it shows that our solution with the permutation matrix actually can take advantage of arbitrary class distribution prior. And the last row shows the most interesting result, where we basically try to estimate the class distribution prior using this method. And it shows that even when we don't know the ground truth imbalance, it can reach to reasonable results. And it, of course, outperforms the uniform class distribution prior. And these are the same results when we increase the imbalance factor to 20, and we see similar trend. This is another interesting experiment where we extend our method to solve a different task, which is novel class discovery. It's a simpler but related problem. And the assumption in here is that the unlabeled data only contain novel class samples. In our case, unlabeled data can contain both samples from known and unknown classes. And we, to extend our method for this problem, we generate pseudo-labels only for novel classes. We report results on CIFAR-100 dataset, where 50% classes are novel. And even on this problem, we see that our method achieves state-of-the-art results by a large margin. So this is some additional analysis. In most of our experiments, we assume that 50% classes are known, 50% classes are novel. So in here, we are trying to see what happens if we vary the percentage of novel classes and compare with second best method UNO. And we see that for both sin class, novel class, and all class performance, our method predictably performs well. And so to summarize, in this work, we propose a streamlined solution for open-world semi-supervised learning, which only requires a single objective function. We also proposed a simple method for estimating number of novel classes. Our proposed method can naturally handle arbitrary class distribution. And it can be extended to solve the related novel class discoverators. And we also outperform current state of the art on multiple benchmark datasets. So this concludes our third work, that is towards realistic semi-supervised learning. However, like all works, this work has some limitations. So one of the major limitations in here is that we assume that the novel class samples are available during training. However, this is a very difficult constraint to satisfy in real world scenario, because for real classes, we might not have samples. And also we assume that the set of novel classes is fixed, but during inference, we might encounter new novel classes. On the other hand, human can learn new concepts with only a few examples, and future learning tries to mimic that capability. Therefore, next we focus on future learning, and I'll talk about our work, which is invariant and equivariant representations for future learning. This work was published in CVPR 2021. So before going into solution, let's look into the dominant approaches for future learning. So one of the dominant approaches is optimization-based meta-learning. The main idea in here is to apply gradient-based update to come up with some good set of initial weights, which can be quickly adapted in presence of new classes. Another set of methods are metric-based meta-learning, where the objective is to come up with a good generalizable metric space, where, let's say, for new classes, the class assignment can be performed using nearest neighbor assignment. Now, there are a new set of works which does not do meta-learning, which are transfer learning-based future methods. And this work basically are motivated from this insight from this work, where it kind of depicts that the quick adaptation is in meta-learning method crucially depends on feature reuse. So actually, it's not the adaptation part, it's what features you learn. So in this method, what happens is that we can train a baseline feature extractor on all the label data. Then during inference, to recognize new classes, we can simply use a nearest neighbor or a linear classifier. And surprisingly, these methods actually achieves comparable performance to state-of-the-art meta-learning-based methods. Therefore, the objective of this work is to improve future learning performance by simply improving the base feature extractor. To do that, let's investigate the inductive biases in CNN to improve this base feature extractor. So what are inductive biases? So inductive biases basically reflects kind of our preference for one set of particular solution. And there, the examples of inductive biases are ubiquitous in deep learning. So for example, let's say the convolution operation basically bakes the translational equivariance bias. Then we have the local neighborhood relevance baked into the pooling operation. So max pooling, average pooling, and there are different sparsity implemented through different regularization terms like L1. So in this work, we focus on two broad classes of inductive biases, which are invariance and equivariance. So if we think about it, there are different kinds of invariance in CNNs, and because invariance provides better class discrimination because it leads to compact class boundary. However, it does not achieve optimal generalization performance because the goal of invariance is to have compact class boundary on the known classes with the known set of label samples. And the common example of invariance in CNNs would be invariance to different nuisance factors like natural perturbation, viewpoint changes, or image transformation. Equivariance, on the other hand, helps in learning better transferable features by encoding the structure of the data better, which leads to better generalization performance. However, equivariance is not optimal for class discrimination because it does not explicitly tries to have compact class boundary. Common example of equivariance is basically builds upon the idea of generalizing equivariance. So it would generalizing translational equivariance. So it would be equivariance to translation, reflection, rotation on other generalized transformation. So in this work, we want to combine these complementary strengths of both invariance and equivariance. So basically to have better class discrimination and better transferable features. And our hope is that this kind of generic features will improve generalization for future learning. To be particular, we want to enforce invariance and equivariance to a general set of geometric transformations, so which would be affine transformation or similarity transformation. However, enforcing invariance and equivariance to a continuous set of parameters is difficult to optimize. Therefore, in this work, we quantize the space of geometric transformation for easy optimization, and we solve this in a multitask learning framework. Now let's look into our solution, how we enforce invariance. So it's the implementation is very simple. So we basically enforce transformation invariance to instance classification. For that, we incorporate an invariant head. After that, we leverage contrastive loss for instance classification. So basically, the goal is to map differently transformed copies of the same image together. And we find that drawing negative samples for contrastive loss from memory bank actually improves convergence and performance. So this is basically loss function. So in here, basically for enforcing invariance, we are looking into average contrastive loss over M transformations for samples. And if we look at the definition of contrastive loss, so basically in here, we are trying to maximize the similarity between one transform copy, VM, and the reference image, VR, and while trying to minimize the similarity with the negative samples. So this is basically how we implement it. Let's say we have a set of images, we create M transform copies, pass them through a feature extractor F theta, then we pass those features to invariant head F omega, and we compute contrastive loss on those representations, and we also draw negative samples from a memory bank. For enforcing equivariance, we perform transformation classification. So for that, we incorporate an equivariant head, like as mentioning before, this solution works in a multitask learning framework. And it does not require any manual supervision because we can create proxy levels because we know what is the input transformation we are applying. And it ensures that the output embedding retains the transformation equivariant features. And basically, the objective function is a cross entropy loss where we're trying to classify the input transformation. So how this works is basically for each sample, we are creating M transformation copies. We pass them through the feature extractor F theta. Then we pass them through the equivariant head F psi. And after that, we perform MOA transformation classification. In this work, we also incorporate multi-head distillation to learn better features. So basically, what happens in self-distillation is that it learns from smooth prediction from the teacher, which basically encodes inter-label dependencies. However, in this work, it's not only the classification labels we are looking into. We have also two other objectives, which are invariance and equivariance. So we extend this idea to multi-head distillation, which ensures that the transfer of learned invariant and equivariant representation between the teacher and student. To be particular, we perform KL divergence loss. We compute KL divergence loss between the outputs of the supervised classifier head. We compute KL divergence between the outputs of the equivariant head because it's probability distribution. Since the output of the invariant head is not a probability distribution, to distill the knowledge, we compute L2 loss. And this is the overall loss for knowledge distillation, which is basically summation of these three loss functions. So this is our overall method, where given a set of images, we create M transform copies. We pass them through the feature extractor F theta. Then we compute invariant loss, which is contrastive loss on top of the invariant head F omega. We compute the classic transformation classification ahead to enforce equivariance on top of the equivariant head F psi. Also compute the regular supervised classification loss on top of the classification at F phi. This is our overall solution with distillation. Where given a teacher model. So basically, this is the teacher model. In parallel to these three losses, that means classification, invariance, and equivariance, we also have three objective functions, which is the KL divergence between the equivariant head, then L2 loss between the invariant head, and KL divergence between the supervised head. And this is basically the objective function, which is basically summation of all these losses. So cross entropy for the supervised classification, and the equivariant and invariant losses, and the knowledge distillation loss. So here are some results on CIFAR FS and FC100 dataset. So these datasets are specifically modified for few shot learning, which are which are variant of CIFAR 100 dataset. So in here, I'm showing results on CIFAR FS dataset. So how this experimental setup works is we train on a set of classes. So in case of CIFAR S, it would be 60 trained classes. Then we evaluate on 20 unknown classes, for which we have only 1 label samples or 5 label samples. And this classification, we are performing 5-class classification. So we observe that in here, our numbers are reported in red, and the second best is blue. And we observe that compared to the second best, we have significant improvement. We see larger improvement on FC100. So in case of this 5-shot, we probably outperform around 5%. We also report results on mini ImageNet dataset, which are basically 100 classes from ImageNet. We also see good improvement in here. We also report results on TRD ImageNet dataset, which has around 600 classes, more than 600 classes from ImageNet. And we also see noticeable improvement in here. So this is an interesting result, which in here we report results on a metadata set, which is newly proposed. So how this experimental setup works is We train on a training split of ImageNet, then we test it on validation set of ImageNet and also 9 other data sets. And in here, like in all these settings, we evaluated on 1 shot or 5 shot. In here, the number of shots is variable, and also the classification, that means number of classes is not 5, it's also variable. And in this challenging evaluation case, we see that we outperform the previous best method with noticeable margin. So if we think about it, how we implemented the idea of invariance and equivariance are using self-supervised losses. So to have a more competitive comparison with other self-supervised losses, we compare with popular self-supervised objective like solving jigsaw puzzle, location prediction, context prediction, or rotation prediction. And we observe that compared to all these solutions, our principal solution has much better performance. And we also extend this idea to the case of supervised classification and have some interesting results. So we see that if we just use the supervised baseline on CIFAR 100 data sets, so this would have been the error rate. However, if we apply both invariance and equivariance, we see substantial improvement. This kind of validates that the idea we have about invariance and equivariance is also valid for supervised, but it is more prominent and significant in case of few-shot learning because we are dealing with novel classes. So to summarize, in this work, we simultaneously enforce equivariance and invariance that leads to better class discrimination and better transferable features. Our implementation is simple. It does not require extensive architectural changes. We introduce multi-head distillation, which leads to further improvement. We also outperform current state-of-the-art few-shot learning-based methods on multiple benchmark datasets. So this concludes our final work, that is invariant and equivariant representations for few-shot learning. Now to summarize this dissertation, in the first work, we talk about uncertainty-aware pseudo-label selection for semi-supervised learning, where we improve pseudo-labeling for semi-supervision by incorporating uncertainty. Our solution is domain agnostic and can be easily used for multi-label classification, and we also achieve competitive performance. In the next work, we extend semi-supervision to uncurated open world setting, and we develop a solution in which we can perform end-to-end training without relying on self-supervision, and our proposed solution has lower computational cost. In the next work, we propose an improved solution for open world semi-supervised learning, where our proposed solution requires a single objective function. We also propose a simple method for estimating the number of novel classes, and our proposed method can naturally handle arbitrary class distribution. Finally, in the last work, we focus on few-shot learning, where our proposed training mechanism leads to better class discrimination and better transferable features, and our proposed solution is simple in implementation. And here are some potential directions that can be explored from this work. So for improving pseudo-labeling for semi-supervised, we can look into performing pseudo-labeling for long-tail data. So to give more context, in most of the pseudo-labeling based methods, actually it works on uniform data, and performing selection on uniform data is easier, but scaling that for long-tail data is non-trivial. So exploring that would be interesting. Another issue with pseudo-labeling is that error accumulation with long training. So to avoid that, in our work, what we do is we do cold restart. That means after each pseudo-labeling step, we reinitialize the network weights and continue training. So a principal solution for this would be better. Then we can also improve open world semi-supervised learning. So even though we have a solution for estimating the number of classes, it's separate from the representation learning. So better solution would be to do simultaneous novel class estimation and representation learning. Also, like I mentioned before, the current open world semi-supervised learning methods assume that the number of novel classes is fixed. However, in real world, it has to be dynamic. So an online solution or continual learning solution for open world semi-supervised learning will be interesting. And another in the current open world semi-supervised learning, even though we assume that the known and unknown classes are disjoint, but they are kind of formulated from the same data set. So it would be interesting to see what happens if the novel classes are drastically different. That means if they come from a cross domain. So it can be extra geospatial data. So whether we can still take advantage of the known class information. And for few-shot learning, we can explore the idea of invariance and equivariance for other architectures. In here, we only export for CNN, so we can explore for transformers. And as we all know, the large vision language models are becoming increasingly popular, and they have very good in-context learning performance. So exploring how can we improve that just from from simple feature learning would be also an interesting direction. So these are some set of publication I was able to be part of during my PhD, and thank you.